everyone. Today we are going to talk about position time functions as they relate to mass and spring systems. And we're also going to discuss pendulums and the transformation of energy within pendulums. And then finally, we're going to wrap up with some discussion on waves and wave behavior. So let's go ahead and get started. When we're looking at our graph of our simple harmonic motion of our spring. Say we have this hanging spring and it's bouncing, it's going down and up and down and up. So here, right here is our equilibrium point. And so then it goes up and then it comes back down towards equilibrium point, and then it goes down away from equilibrium, and then there's this restoring force that brings it back to equilibrium, away from equilibrium, restoring force restores it back to equilibrium, and so on and so forth. So that's your harmonic motion, your simple harmonic motion. It's this repeating pattern. And so you'll see here, I have this equation, y equals a sine omega t, and that equals a sine square root of k over m times t. But really, just in looking at that, I want you to see this diagram and then looking at these two notes. For an object that's starting from your amplitude, your maximum displacement, for that point, you really actually have a cosine graph. Okay, you have a cosine graph. So you're going to have something where your maximum is going to be starting from or your 0 point is going to be starting at your maximum. So you have something like this. Okay. And those ones are the easier ones to deal with. And when you look at your equation, x equals x being your displacement. So really what I've labeled as y here. So your x is equal to your amplitude cosine omega t, where omega t is equal to 2 pi frequency. And we solved that in one of our more recent videos. If your object is starting from equilibrium, then you're going to use this a sine omega t, where again, omega is 2 pi frequency. Okay, so that's how you're going to find the function, the equation of your simple harmonic motion spring mass system. Okay, and so we're going to go ahead and take a look at a sample problem, because this is something that I really feel like we can't do without really looking at a problem. So we have a 0.5 kilogram object is attached to a spring with a spring constant of 30 newtons per meter. So that's your spring constant, and released from rest at t equals 0 from a position of 0.25 m. So in this case, because it's released at your maximum, you know that you're dealing with x equals a cosine omega, which is your 2 pi frequency time. Okay, that's going to be your equation. Okay, and so when you look at that, okay, what is your amplitude? Your amplitude is 0.25. So x equals 0.25 cosine, and then 2 pi frequency. So we don't know what our frequency is, and that's what we have to solve for. So our frequency, well, we know our period is equal to 2 pi square root m over k. Okay, and so our frequency is going to be the reciprocal of that. So our frequency is 1 over 2 pi square root m over k. Okay, and so when I go ahead and plug in my mass is 0.5 and my k is 30, I get 1 over 2 pi square root 0.5 over 30. Okay, and then that ends up giving me a frequency that is equal to 1.23. Okay, so that's equal to 1.23 hertz. And so I end up getting, my equation is 2 pi times 1.23 times time. Okay, so the equation, or my location x as a function of time, is going to be equal to 0.25 cosine, and that's going to be cosine 7.73 time. Okay, and this is going to show up, this type of equation or question is going to show up in your next practice problems for class. So what I would like to do is I would like to take a look at our next question. Okay, our next question is: the motion of a 2 kilogram oscillating object is described by the following equation: 0.5 sine 1.5 pi t. All of the variables in the function are measured in standard units. So find the amplitude. Well, I am looking at this equation and my amplitude is going to be given there. So my amplitude equals 0.5. Okay. And then it says, and that's going to be in meters, and it says find the period of motion. Okay. Well, the period of motion, what do I know? Well, I know x a sine, so this is x equals a sine. So if we stop and look at that, what are we talking about? We're talking about something that starts at equilibrium. A sine, and then we have 2 pi f t, right? And so here we know 2 pi f is equal to 1.5 pi. Okay, so our pi can cancel, and we have 2f equals 1.5. So frequency is equal to 1.5 divided by 2. And so frequency is going to be equal to 0.75. But the question is not asking that. The question is asking for period of motion. So that's in hertz. And we know that period is equal to 1 divided by the frequency. So that's going to be 1 divided by 0.75, okay, which is going to be equal to 4/3, which is 1.33 seconds, okay? Okay, so now this next question says, find the object's kinetic energy and potential energy when the object is located at a position of x equals 20 centimeters. So what do I know? Well, I know that my mechanical energy, which is my total mechanical energy, is 1/2 Ka squared. And that's equal to my potential energy, which is 1/2 Kx squared plus my kinetic energy. And since I'm being asked what my kinetic energy is, I don't have to write out that equation. The potential energy and the kinetic energy are going to add together to give you your total mechanical energy. Now, the potential energy and the total mechanical energy are going to require you to know the K value, or the spring constant. So how are we going to figure out the spring constant? We're going to look at, first, we need to look at, we know the period. Period equals 2 pi square root m over k. Okay, and so we know that our period squared divided by 4 pi squared is equal to m over k. And so then our k value is going to be equal to 4 pi squared m, which is going to be 2 kilograms, divided by t squared. And our t is going to end up being 1.33, and square that. So that's going to end up giving us a value for K to be 44.6. So the next step is going to be to figure out what my 1/2 Ka squared is. 1/2 Ka squared is going to be 1/2 that 44.6 times my A, which is going to be 0.5 squared. Okay, And then that's going to be equal to my potential energy, which is 1/2 K. My K value is 44.6. And my X value in this case, is going to be 0.2 meters squared plus kinetic energy. So I end up getting that my potential energy is going to be equal to 0.892. My potential energy is going to be equal to 0.892. And my total mechanical energy is going to be equal to my one half 44.6 times 0.5 squared. I'm going to find the difference there, and I end up getting my kinetic energy is going to be equal to 4.68 joules. Okay. So now we're going to go into a discussion on pendulums. The pendulum, we remember hopefully from our energy unit, so this should be pretty quick. The pendulum is a simple harmonic oscillator. It goes back and forth, and it plays off of the idea of the laws of conservation of energy. The displacement needs to be small, though, for it to work properly, and that's because you want to have a restoring force, but you don't want to have any kind of like friction or anything that's going to cause it to not have that constant motion. Okay. So when you look at your pendulum, you have a restoring force. Your restoring force is going to be pulling that pendulum back into the center of that equilibrium position. So when you're looking at that, your equilibrium position is going to be down here at your minimum. So you're going to be coming back down to equilibrium and away, and then to equilibrium and away. Okay. So that's kind of what's going to end up happening with all of the scribble. Okay. So pendulums. One way to look at a pendulum, for a pendulum to be considered that simple harmonic motion, you need to have a restoring force proportional to the displacement from the equilibrium. And so that restoring force for a very small angle, your sine theta, is equal to x divided by L. So when we start to manipulate this equation, mg times x over L, and we know that force is equal to kx, we end up finding that the period of a pendulum is equal to your 2 pi square root L over G, okay, using the simple harmonic function that we used for a spring. So we have that the period of a pendulum is equal to 2 pi times the square root of L over G. It's important for you to recognize what values are in this equation and what values are not, what variables. So for example, the length of the pendulum is going to affect the period. The gravity is going to affect the period. So my period of motion for a pendulum is going to be different on Earth than it is on the moon or on Jupiter or Mars or Saturn, okay? However, your mass, if I change the mass, I've got a very massive object or a very light object, the mass is not going to change that period of the pendulum. Pendulums are going to obey the conservation of energy. And that's why I said we've already covered this stuff. But looking at equilibrium position and your maximum displacement, at your equilibrium position, your height is going to be basically 0. Okay, you're setting that as your 0 point. So you have a low potential energy and a high kinetic energy. Equilibrium position, high kinetic, low potential. Maximum displacement, high potential, low kinetic. And you want to look at it as if your maximum displacement is going to be your highest height, and that's why. So you've got your MGH. But it is important for you to understand that the total energy of an oscillating system is going to be constant. So let's look at this next practice problem. It says calculate the length of a long pendulum that completes 12 full oscillations every minute. Start with our period. Our period, T, is equal to 2 pi times the square root of L over G. So we have our 2 pi square root of our L divided by our G. I square everything, I get T squared over 4 pi squared, and that's going to be equal to L over G. Going to end up having 12 cycles per minute. 12 cycles divided by 60 seconds. That's going to be 0.2 cycles per second. So my T is going to be equal to 1 over my frequency, because that's a frequency. And my frequency I have is 0.2. So my period is equal to 1 divided by 0.2. Okay, and that's going to end up giving me 5 seconds. So then I end up getting L is equal to GT squared divided by 4 pi squared, and that gives me G times 5 squared divided by 4 pi squared. So when I plug all of that in, I end up getting 6.21 meters for the length of this pendulum. Now, we're going to transition into waves, and the next few moments are going to be just covering concepts for waves. So when I'm looking at a wave, what a wave is a wave is a traveling disturbance that's going to carry energy from one place to another. A wave does not carry matter. A wave is just carrying energy. And for every wave, the wave is caused by a vibrating source. So what can do that? Like I can hit say I were to hit a pole, there's going to be a wave that's going to transfer from one end of that pole to the other. And because I've applied a force, I've allowed some kind of disturbance. Okay. Resonant frequency is your natural vibrating frequency. So that's going to be, if you think about it, if you've ever heard of like an opera singer singing and breaking glass or something, when the resonant frequency is matched, your natural vibrating frequency, it's going to cause the glass to shatter. Now, a wave is not matter, but the wave pattern can travel within matter. It's just not transferring matter. So those are just some basic details about waves for you. So some more wave properties. Think about the last time you played a guitar or a violin or you saw a string instrument. A string instrument is going to let out a certain sound, and that sound is going to be let out based on the way that that wave is traveling down the spring or down the string. So in terms of wave properties, things that we need to know the amplitude, okay? How large is the disturbance? What's the wavelength, the period, the frequency, and the wave velocity? We can determine the wave velocity as the square root of the force of tension within your string divided by your linear density, or the mass of the string divided by the length of the string. I am not going to test you on that information, but I do think that it's important for you to understand that your velocity of the wave is going to change based on the tension. So the higher the tension, the faster the wave is going to transfer. And so the reason I want you to know that is because when you're tuning a guitar, that's what you're doing. You're changing the tension within the guitar strings. So there are two different types of waves. We have mechanical waves and we have non-mechanical waves. A mechanical wave is a wave that requires a medium or requires substance to travel through. That's going to be like a wave on a string or a wave in water or a sound wave. Sound needs a medium to transfer through. So sound, you're not going to hear something where there is no matter, okay? But you will hear something when there is matter. So for example, if you were yelling in space, you're not going to hear something as well. Okay. But then if you're yelling down a tube of something, then you're going to hear pretty well. Okay. And sound is actually going to travel faster through solid than liquid than gas. And so that's why, like, if you're showing a house and you live by a busy street, the best time to sell is on a dry day, because on a dry day, sound isn't traveling as fast. And so people aren't going to hear that road noise as much. If you show a house on a wet day, that's going to cause the people to be able to hear any amount of road noise that's there. Okay. Test it out the next time that it's raining outside. Go outside and you can hear a difference in the sound outside, all based on the moisture within the air. Now, non-mechanical waves like light do not require a medium. Okay. So light will travel in a vacuum. So we can split our waves into two different types of waves. We have longitudinal waves and we have transverse waves. Longitudinal waves are the waves in which the vibration is going to be, the particles are going to vibrate parallel to the motion of the pulse. Okay. So you can see this in this slinky right above you. You can see that slinky right there, and your pulse is left to right, and your disturbance is left to right. Okay. This is a parallel or a longitudinal wave. This is the type of wave that sound travels. Now, transverse waves are what you kind of draw. You draw your amplitude and you draw your wavelength. When a teacher is showing you a wave, they're typically going to draw a transverse wave. And it's where your disturbance is perpendicular to the direction of the wave pulse. Okay. Electromagnetic waves like radio waves and light waves are an example of that. So here is a diagram of the difference between a longitudinal wave and a transverse wave. Okay. In a longitudinal wave, you have this compression, rarefaction. Compression is where everything is close. Rarefaction is where everything gets farther apart. And you've got the energy transport is in the same direction as the disturbance. Whereas for a transverse wave, the energy transport is perpendicular to the disturbance. So things that you need to know about a wave. We've already discussed wavelength, but wavelength is the distance that a wave repeats itself. The period is the amount of time one wave is going to need to pass a given point. The frequency is going to be the inverse. It's going to be how often the wave repeats itself. So cycles per second, or hertz, or 1 per second. Now, it's important for you to recognize that the period and the frequency are inverse of each other. So period is equal to 1 divided by frequency, and frequency is equal to 1 divided by the period. So then how do we find the speed of a wave? Well, it's very important for you to go back to speed and what you know about speed. Speed is going to be your distance divided by time, correct? So if speed is distance divided by time, we're looking at our distance of our wave divided by the time. Well, our distance is our wavelength, right? And our time is our period. What's the inverse of period? Frequency. So the velocity of a wave is equal to the wavelength of the wave times the frequency. You might remember this from previous classes where you looked at the speed of light is equal to the wavelength of the light times the frequency of the light. So let's take a look at this example problem. We have a wave completes a full cycle of motion in 0.35 seconds. If the wave travels 10 meters in that amount of time, calculate the wave's speed. So our distance, our x, divided by our time. And our x is going to be equal to our 10 meters. And our time is going to be equal to our 0.35 seconds. And that's going to end up giving us a value of 28.6 meters per second. 28.6 meters per second. So what are the wave's frequency and wavelength? Well, when we look at our frequency is 1 divided by our period, and our period of time is 0.35. So we're going to figure out that our frequency is going to be equal to 1 divided by 0.35, 1 divided by 0.35, and that's going to end up giving me a value of 2.86 hertz. And then when I'm looking at my my wavelength is given to you in the question as 10 meters. So when you have a something that is fixed, a wave pulse that is going down, say, a string that is fixed. Think about your guitar, for example, in this situation. In a fixed end boundary, the end of the medium will not be able to move because the mediums can be attached to something. So what's going to happen? Well, when I send my pulse down, my new pulse coming back is going to be reflected downwards, and it's going to be going the same velocity. So the reflected pulse has the same speed, the same wavelength, and the same amplitude. It's just going to be reflected. So this is what it's going to look like for a fixed end system. Like, think about like a guitar string, okay? Now, what if you have a free boundary? A free boundary would be like I've got like a ring around it where a ring is allowing it to move up and down. What's going to happen? Well, my reflected pulse is going to come back not inverted, so going the same direction. It's going to be identical to your incident pulse, except it's going to be moving the opposite direction. So it goes up and it comes back. It goes down and it comes back. So this is when you send a pulse or a vibration down a wave. Now, what if you change the medium? Because if you change the medium, then the wave is going to be able to transfer different, correct? At this point, a wave pulse will transfer from one medium to another. So if I'm going from less dense to more dense, I'm going to have a reflected pulse come back inverted, and a transmitted pulse, the pulse that goes through, is going to go the same direction, non-inverted. So you have part of the wave energy is going to be transferred to the more dense medium, and part of it is going to be reflected. Transmitted pulse is upright, the reflected pulse is inverted. Now, the speed and wavelength of the reflected pulse is going to be the same, but the amplitude is going to decrease because energy is associated with the amplitude. The speed, wavelength, and amplitude of the transmitted pulse are all going to be smaller than the incident pulse or the pulse going in. So here's an animation for that. So the wave transfers from low density to high density material. This is what we see. The transmitted wave speed decreases, amplitude decreases, wavelength decreases, and the polarity is the same. The reflected wave, the polarity is reversed, it means that it's inverted. The amplitude decreases, the wave speed and the length remains the same. Now, what if I transfer from high density to low density material? Whoa, that's going to be a change. So you're going to end up having a transferred, or your transmitted pulse is going to have a much higher amplitude. So the transmitted wave is going to have an increased amplitude, wave speed is going to increase, the wavelength will increase, and the polarity is going to remain the same. So it's not going to be inverted. The reflected wave, the wavelength and speed stay the same, but the polarity remains the same and the amplitude decreases because you've transferred some of that energy